Hello friends, up till now we have studied about the aliphatic nucleophilic substitution reaction and its types. In our previous lecture, we have learned about what is meant by SN1 reaction and what is its stereochemistry. It means when we use optically active substrate, we know that we will obtain racemization, and in that racemization we obtain inversion of configuration as a major product. Now in this particular lecture we have to study about the SN2 reaction. Now it is one of the type of aliphatic nucleophilic substitution reaction. Now SN2 reaction is nothing but the bimolecular nucleophilic substitution reaction. It is nothing but bimolecular nucleophilic substitution reaction. As being bimolecular nucleophilic substitution reaction or as being bimolecular in nature, the rate of this reaction depends upon the concentration of both the reactant, that is concentration of alkyl halide as well as on the concentration of nucleophile. And we know that generally we used aqueous KOH or NaOH as a nucleophile in SN2 reaction. Now, in case of SN1 reaction, we know that the alkyl halide which we used as a reactant is bulky in nature, whereas in case of this SN2 reaction, the alkyl halide which we used as a reactant is less bulky in nature. For example, lower alkyl halides generally used as a reactant or substrate in SN2 reaction. Now we move towards the reaction of SN2. Now consider an example of methyl bromide. When treated with aqueous NaOH solution, we will obtain methyl alcohol as a product. Now we know that this is methyl bromide. When this methyl bromide undergoes hydrolysis with aqueous NaOH or KOH, here we use NaOH solution. The nucleophilic OH negative ion attack on the carbon of this alkyl halide to give methyl alcohol as a product. Now we have already seen that the rate of this reaction depends upon the concentration of alkyl halide and nucleophile. That's why it is second order in reaction. Hence we move towards the kinetics of this reaction. In case of this kinetics, we determine the rate of that particular reaction. Now we know that the rate of SN2 reaction is directly proportional to the concentration of alkyl halide as well as concentration of nucleophile. We have already taken an example of methyl bromide and NaOH. That's why we draw the rate of our example and write its equation as rate is directly proportional to methyl bromide and NaOH. Now this rate is equals to K, which is nothing but the rate constant, and concentration of both the reactants which we used in our SN2 reaction. Now, on the basis of concentration of these two reactants, we may say that the SN2 reaction is second order. This SN2 reaction is second order in nature. Now, this is all about the kinetics of a reaction. Now, we have to move towards the mechanism of this SN2 reaction. While dealing with the mechanism of SN2 reaction, we already seen an reaction when methyl bromide is treated with NaOH. Now we have to see the mechanism of this reaction. This is the methyl bromide. We know that in case of SN1 reaction, the mechanism or that SN1 reaction proceed in two steps, in which formation of two transition state occurs, whereas the SN2 reaction proceed via concerted mechanism. It means in case of SN2 reaction, the simultaneous making and breaking of bond takes place. The simultaneous making and breaking of bond takes place. That's why we say that the mechanism of SN2 reaction proceed via concerted fashion. Now, on that basis, we say that when this nucleophile attacks on the carbon atom of this alkyl halide then we obtain this transition state in which as soon as this OH negative tries to attack on the carbon atom of this alkyl halide, at the same time this Br atom tries to depart from this molecule, and we obtain a transition state which is shown as this is this transition state in which as soon as this OH negative try to attack on this carbon atom. At the same time, this bromine atom tries to depart from this molecule. Now look at this. These two bonds, that is bond between carbon and incoming nucleophile, that is OH negative, and the bond between this carbon and outgoing nucleophile, that is Br negative atom, are partially shown, are shown by dotted lines. It means when this carbon oxygen bond is formed, when this oxygen tries to form, or when this OH ion, OH nucleophile tries to form a bond between this carbon and OH group, at the same time this Br atoms tries to depart from this molecule. It means it proceeds via the concerted fashion. Now this is the first step, which is endothermic in nature. The amount of energy which is required to form this bond is further utilized to break this bond. Hence, this step, that is this first step, becomes slow, and as it becomes slow, it means it is the rate determining step of this SN2 reaction. And now this second step is obviously fast, in which this halogen atom completely removes and this OH form a bond with this, and we obtain this methyl alcohol as a product. Now this is all about the mechanism of SN2 reaction. Now on the basis of mechanism, we have to draw the energy profile diagram of SN2 reaction, and we also know that the energy profile diagram is plotted against potential energy against reaction coordinates. Now we have to see energy profile diagram of SN2 reaction. We know that the energy profile diagram is plotted against potential energy, which is increases in this direction, and reaction coordinate. We know that this is the first energy level at which is nothing but, it is the first energy level which is nothing but the energy of our reactant. Now this is the energy of reactant, and we know that we used methyl bromide as a reactant. As the reaction starts at this position, the attack of a nucleophile at this certain position, nucleophile tries to attack. When nucleophile tries to attack, the energy of the reactant increases to this level, and this is nothing but the transition state of SN2 reaction, that is transition state. At that transition state, we know that the molecular the intermediate which we obtain has the valency of carbon atom as 5, and this transition state, the intermediate at this transition state is like this. The intermediate is present at this transition state. Now, when the transition state is achieved, the energy of the system begins to decrease. The energy of the system begins to decrease, and the formation of product is formed as a methyl alcohol. This is the energy of product, and this is the energy of reactant, and this is the energy of product. This is nothing but the energy of activation, that is delta E, and the difference in energy between energy of reactant and energy of product is nothing but delta H. Energy of delta H. In case of our SN1 reaction, I have told you that in case of SN1 reaction, the attack of nucleophile occurs on the reactant from the front side as well as from back side. But in case of this SN2 reaction, only the back side attack of nucleophile takes place on any reactant. Then a question will arise, why any nucleophile in case of SN2 reaction tries to attack from the back side only? Why in case of SN2 reaction nucleophile always attack from the back side of a reactant? We know that this is our reactant. If we take any reactant or any alkyl halide in case of SN2 reaction or any SN2 reaction, there exists a leaving group. Here in this case, this bromine is a leaving group. Now this bromine which acts as a leaving group here, will create a steric hindrance, to upcoming nucleophile. It creates a steric hindrance to upcoming nucleophile. That's why to avoid this steric hindrance generated by this leaving group, the incoming nucleophile in any SN2 reaction generally tries to attack from the backside. This nucleophile generally avoid this steric hindrance, to attack from the backside. That's why each and every SN2 reaction or each and every reaction which proceed via SN2 mechanism has backside attack of nucleophile, and due to that backside attack of nucleophile, in each and every case we obtain inversion of configuration. It means if, for example, if we use the optically active reactant, and that the carbon atom of that optically active reactant has R configuration, then when we determine the configuration of product after the attack of nucleophile or after the attack of SN2 reaction, and we observe the configuration of carbon atom, optically active carbon atom from product, then we noted that the configuration of carbon atom in case of reactant is totally different or is inverted in case of product, which we have to see in our next lecture, that is stereochemistry of SN2 reaction. Thank you.